Welcome to the Jeep Dive. Today, we're heading out beyond our atmosphere. We're going to explore the compelling and sometimes disruptive world of space weather.
Right.
What is it exactly? Well, you can think of it as the conditions out in space, especially near Earth, that can mess with our technology, both the stuff in orbit and, right here on the ground. And to really get a grip on its power, we're zeroing in on one specific event, a real jolt from the cosmos, you might say.
Yeah.
And this feels pretty timely, actually, because there's this fantastic new free space physics course online. It's at www.spaceinfo.clublearn. Designed for everyone, really, whatever your background.
That's a great resource.
So our goal today, let's really dig into the details and understand the lessons from one particularly intense geomagnetic storm.
That's right. And, when we talk about storms that really made an impact, the March 1989 event definitely stands out. It wasn't just some scientific curiosity. It had real, tangible consequences. It really pushed us, I think, to recognize how serious space weather can be.
A wake-up call, almost.
Definitely. It forced a reevaluation of how we understood the risks.
Okay, so let's start at the source then. Where did this dramatic event actually begin? It wasn't just an average day on the sun back then, was it?
No, not at all. Early March 1989 saw a really significant surge in solar activity. There was this particularly large, very energetic group of sunspots, active region 5395 it was called.
Okay.
And that was the source. On March 6th, this region just unleashed an X-15 class solar flare.
X-15, wow. What does that mean in simple terms?
Well, X-class flares are the biggest category, the most powerful ones, and an X-15, that's a real powerhouse even within that top category. Reading about the sheer energy involved in the sources, it's pretty mind-boggling, almost hard to picture.
An X-15, to the sun really letting loose. And what happened after a flare that big?
Well, that huge flare, it was also accompanied by a fast-moving coronal mass ejection, a CME.
Right, the CMEs.
Right. Yeah, imagine just a gigantic bubble of plasma and magnetic field erupting from the sun's outer atmosphere, the corona. And this particular one was moving incredibly fast.
How fast are we talking?
Fast enough to make the journey from the sun to Earth in just over 3 days.
3 days. So this enormous cloud of solar stuff is just hurtling towards us. What happens when it finally gets here?
So on March 13th, 1989, the CME slams into Earth's magnetosphere.
Our magnetic shield.
Exactly, our planet's protective magnetic field. And that impact, well, it triggered a severe geomagnetic storm. It actually reached the highest level on the scale we use, the KP index, a KP of 9.
KP 9, that sounds extreme.
It is. It signifies extreme intensity. The collision basically squashed our magnetic field, compressed it, and crucially, it generated these incredibly powerful electric currents way up in the upper atmosphere.
Okay, and these currents high up.
Yeah.
That's where the trouble started down here, isn't it? Especially with the Quebec blackout.
Precisely. Yeah. The most significant and widely felt consequence of that storm was the sudden collapse of Hydro-Quebec's power grid.
Sudden is right. I read it was incredibly fast.
It was. The entire system shut down in, get this, just 90 seconds.
90 seconds for a whole power grid.
90 seconds. That speed.
Yeah.
It just highlighted a critical vulnerability, how interconnected and, frankly, how sensitive our modern power infrastructure is to these kinds of external shocks.
Wow.
It wasn't just equipment damage initially. It was the cascade failure set off by that sudden surge, a lesson we're still, grappling with in other complex systems, too.
90 seconds. That's almost hard to believe. What was the actual mechanism? What caused such a rapid failure?
The main culprit was something called geomagnetically induced currents, GICs.
GICs.
These are electric currents that flow through the Earth's surface itself. They happen because the magnetic field is changing so rapidly during the storm.
Okay.
And these ground currents, they look for paths of least resistance. So they found their way into conductive things, like, in this case, Quebec's long power transmission lines. And this huge influx of GICs just overwhelmed the system. It damaged some big transformers, but critically, it also disabled the protective relays.
The safety systems.
Exactly. The things designed to prevent overloads and failures. It's almost counterintuitive, isn't it?
Yeah, it really is. Were there any warnings? Did they know these systems might be vulnerable to that kind of current?
That's a really important point. The understanding of GICs was definitely growing back then, but the specific thresholds, like at what point these relays would malfunction on such a massive scale, that wasn't fully appreciated. The sheer size and the rapid changes in the magnetic field during the storm likely just went way beyond what those systems were designed to handle. It was a harsh learning experience about the extreme limits of space weather.
So the safety net actually contributed to the collapse.
Yeah.
Yeah, that's sobering. And how long were people without power?
It lasted for about 9 hours, and it affected millions of people across Quebec.
9 hours in March.
Yeah, imagine the disruption. No lights, heating problems, businesses shut down. I remember reading one source mentioning hospitals relying on backup generators for that whole time really brings home the impact on essential services.
You mentioned Quebec was particularly vulnerable. Why them specifically? Was it geography or the grid itself?
Yes, several things came together there. First, the geology. The rock under that part of Canada, the Canadian Shield, it's quite conductive.
Meaning the GICs could flow more easily.
Exactly, easier for those currents to travel through the ground. And second, the structure of their grid. Hydro-Quebec has these very long, high-voltage transmission lines stretching over huge distances.
Right.
And those long lines almost acted like giant antennas, effectively soaking up and concentrating the effects of these induced currents.
Right. Makes sense. Now, it wasn't just the power grid that felt this solar punch. Was it satellites, communications? They had issues too.
That's right. It wasn't just terrestrial. Several satellites up in orbit reported different kinds of anomalies. Things like memory faults, sensors acting up. For instance, one weather satellite apparently had some temporary problems controlling its orientation. And even the U.S. Space Shuttle Discovery.
Oh, was it in orbit then?
It was. Mission STS-29. It was in orbit right when the storm peaked, and it experienced some electrical glitches that were later pinned on the intense geomagnetic activity.
Wow. And back on Earth, apart from the huge blackout, any other communication problems?
Yes, definitely. There were reports of intermittent outages, signal degradation in ground-based systems, shortwave radio, for example.
Because that uses the ionosphere.
Exactly. Shortwave relies on bouncing signals off the ionosphere, and that layer of the atmosphere gets seriously disturbed by solar activity, so big disruptions there. And there were also some anecdotal reports about GPS signals being less accurate, maybe less reliable during the storm's peak.
So technology taking hits left, right, and center. But amidst all this disruption, there was also something pretty spectacular visually, right? The auroras.
Absolutely. That was one of the most striking effects, actually. The northern lights, the aurora borealis, they were seen way, way further south than usual.
How far south are we talking?
People reported seeing them in places like Texas, even Florida.
Florida? Seriously?
Places that almost never get a glimpse of the aurora. It must have been an incredible sight for them.
So these amazing, beautiful lights, they're actually a direct result of this whole intense solar storm hitting us.
Precisely. The auroras happen when energetic particles from the sun, carried in the solar wind, but massively increased during things like the CME slam into the atoms and molecules in Earth's upper atmosphere.
Right.
That collision excites the atoms, and they release that energy as light. That's what creates those vibrant colors, the greens, the reds, the shimmering curtains we see.
Amazing. I read somewhere someone in Florida thought it was like a weird electrical storm far off at first.
Yeah, you can imagine. It really shows how unexpected and how far-reaching these effects were beyond just the technological impacts.
Okay, so this storm clearly had a massive immediate impact. But what about the longer term? Did it fundamentally change how we think about and prepare for space weather?
Oh, without a doubt. March 1989 really was a major turning point for space weather research, for preparedness, all of it.
How so?
Well, it gave us undeniable real-world proof of how solar activity could directly and significantly impact our increasingly technological society, our critical infrastructure.
Right. It wasn't theoretical anymore.
Exactly. And in the years that followed, you saw a big jump in investment from governments, from scientific institutions, putting money into better space weather monitoring, more sophisticated forecasting models.
So it basically jolted everyone into action, made us realize this isn't just some abstract science thing, but a real risk to how we live.
Precisely that. And the utility companies, too, around the world, they started taking the threat much more seriously.
What did they do?
They began revising engineering standards, developing specific ways to mitigate the risk to protect their grids better from GICs in the future.
Like what kind of things?
Things like installing special equipment just to monitor GICs, putting procedures in place to operate differently during big storms to reduce risk, and even looking at physically modifying parts of the grid infrastructure itself.
That's really interesting
Yeah.
and helpful to put the '89 storm in context. We often hear about the Carrington event back in 1859. How does this more recent storm stack up against that monster event.
Yeah, that's a really crucial comparison. The Carrington event in 1859 was, well, by pretty much all estimates, a significantly more intense storm, just in terms of the raw magnetic disturbance here at Earth.
Okay.
Back in 1859, our dependence on electricity and complex technology was, minimal.
Right, telegraphs were the main thing.
Exactly. The main impact then was on the telegraph systems. They had widespread disruptions, even some reports of equipment catching fire.
Yikes.
Yeah. So the 1989 storm, while probably less intense magnetically than Carrington, caused more widespread, tangible disruption. Why? Because our modern society is just so critically dependent on electric grids and satellites.
So our vulnerability has increased massively.
It really underscores that, yeah. How our societal weaknesses have shifted dramatically with technology.
So in a way, even a somewhat less powerful solar storm today could cause far more chaos than a truly enormous one did back then.
That's exactly the point.
Yeah.
The 1989 storm became this vital benchmark case. Researchers, engineers, policymakers, they still use it today to model and assess what might happen in future events.
It's a reference point.
A crucial one. It serves as this stark, ongoing reminder that, look, our advanced civilization is fundamentally linked to the sun's own cycles, that roughly 11-year rhythm of activity.
Right, the solar cycle.
And we absolutely need to be ready for its more energetic moments.
So the key takeaway here seems pretty clear. Space weather isn't just, pretty lights or something only scientists worry about. It has a very real, potentially very disruptive impact on our daily lives. And that Quebec storm back in '89 is just such a powerful example of that. Given how much more dependent we are now on all this interconnected tech, it really makes you think, doesn't it?
It does.
About the ongoing efforts, the future challenges.
Yeah.
How do we keep safeguarding our systems from these occasional huge bursts from the sun? It's definitely something we all have a stake in understanding better.
Agreed.
And look, if this deep dive has sparked your curiosity, if you want to learn more about the physics behind all this, we really do recommend checking out that free space physics course. It's at www.spaceinfo.club/C.
Yeah.
Just a fantastic resource to explore these, fascinating and really important phenomena in more detail.